So in this video, what I want to do is to derive the sine and cosine rules of trigonometry. So to set up our notation, I've drawn here a triangle and I've called the angles capital A, capital B and capital C, and I've called the sides facing the angles the lowercase version of the angle. So opposite capital A we have a side of length little a, etc. I've then written down here the sine rule and the cosine rule, so let's just look at each of them in turn. The sine rule says that for a general triangle, the side A divided by the sine of the facing angle, capital A, is equal to the same ratio for any of the other angles and sides. So for example, this ratio is also equal to B divided by the sine of the facing angle B, and it's also equal to this length C divided by the sine of the facing angle capital C. So that's the sine rule. The cosine rule you can think of as a sort of generalization of Pythagoras' theorem. What we have here is we say that this length A squared is equal to B squared plus C squared, the other two sides of the triangle separately squared, but then minus 2 times these two sides, B and C, multiplied by each other, and then in turn multiplied by the cosine of the angle facing A, so capital A here, so the cosine of A, and that's the cosine rule. Now there's clearly nothing special about little a here. We can write out other versions of the cosine rule. We could say, for example, that B squared is equal to A squared plus C squared minus 2 times A times C times the cosine of B. And then there is a third one for little c squared, and I'll let you write that out yourselves. So what I want to do now is I want to recall something about the definition of sines and cosines, and then we are going to derive these rules. And to do that, we're going to go on to a new slide. So what I want to do now is just to recall our definition of the cosine and sine functions, and to do that we draw a unit circle centered at the origin, and if we measure an angle anti-clockwise from the x-axis, which I'm calling here the angle theta, then the coordinates of where this line meets the unit circle, the x-coordinate is the cosine of theta and the y-coordinate is the sine of theta. And this is true for angles which are greater than 90 degrees or greater than pi over 2, angles which, in other words, are not just in the first quadrant. So this is a very useful definition. It's our central definition, and what I want to do with it is to derive a property, and what we want to do is we want to show that, so we want to show the following. We want to show that the sine of, and I'm going to use radians because using radians is much more helpful for calculus, pi minus theta is equal to the sine of theta, and I also want to show that the cosine of pi minus theta is equal to minus the cosine of theta. So to do that, I'm going to make myself a little bit more room. So here are the results we want to show. Here is our definition. So it's helpful to again draw a unit circle. So I'll draw it here, centered at the origin, of radius 1. And I'm just going to draw an angle which I'm going to put here in the first quadrant, but you can put it in any quadrant. And let's think about what it means to consider pi minus theta. Well, if this angle here is theta, minus theta is a reflection around the x-axis. So I take this line here, I reflect it about the x-axis, and I'm going to get a line here. So let me draw that. This is now minus theta. Pi minus theta means I add pi to it. Now, going around a circle means you go through 2 pi, so going through pi means you go through half a circle. So I go through half a circle, and that means that I take this line and I just continue it on here until it hits the circle here. So what I'm going to do is I just take this line and I just continue it up to here, and the angle pi minus theta is this angle here from the x-axis to here. So I'll draw it here in red, and the red angle is pi minus theta. I'll just draw it in with an arrow. So what we see looking at this is that the angle pi minus theta is a reflection of the angle theta about the y-axis. So what we have here is we have a reflection about the y-axis. And then from that we can immediately see where these two results come from. If this line is a reflection about the y-axis of our original angle theta, then it is at the same height above the x-axis, so the y value is exactly the same where this line crosses the circle. So the sine of pi minus theta, which we remember is the y value here, is equal to the sine of theta. It's a reflection about the y-axis, so therefore the x-coordinate is minus the original x-coordinate, so the cosine of pi minus theta is minus the cosine of theta. So from this immediately we see that the relations given above follow. So we have shown why it is the case that sine of pi minus theta is equal to the sine of theta, and we have shown why it is the case that the cosine of pi minus theta is minus the cosine of theta. And what I want to do now is, armed with this, we can look at the sine and cosine rules for general triangles. I'm going to go now onto another slide. So what we're first going to do is to derive the sine rule. So again, I've drawn out the triangle, and I've drawn it with our standard convention of capital letters for the angles and lowercase equivalent letters for the facing sides. And what I'm going to do is I'm going to take here the angle C, and I'm going to drop through it a perpendicular line, so it is perpendicular to the line at the bottom here. And I'm going to say that the height of this dashed line that I've drawn is lowercase h. Now, for ordinary right-angled triangles like this one and this one, we can immediately say what the sine of A and what the sine of B is. So we can immediately say that the sine of capital A is h over little b, and the sine of capital B is h over little a. So I can multiply the equation I have here by lowercase b, and I get little b times the sine of A is h, and here if I multiply both sides by little a, I'd have little a times the sine of b is h. So if both of those things are equal to h, they must be equal to each other. So therefore it follows that b sine capital A is equal to a times the sine of capital B. So therefore the sine of capital A, and now I'm dividing both sides by little a and by little b, so the sine of capital A over little a is the sine of capital B divided by little b. Now the third part of the sine rule, that this is equal to the sine of capital C divided by little c, can be immediately obtained by repeating this technique of dropping a perpendicular here. We could drop a perpendicular here, and we would get that the sine of capital B over little b is equal to the sine of capital C over little c, so we could add it here. Or we could drop a perpendicular here, and we would get that the sine of capital A over little a was equal to the sine of capital C over little c. So in general, we can complete the third part, or the third equality of the sine rule, that this is equal to this, and that this is also equal to sine c over little c, and that this is equal to sine c over little c. I'll let you do that. Now, what I want to do now is I just want to point out that in this triangle here, I have assumed that the angles A and B are acute. And what I want to do on the next slide is to show how we can also derive the sine rule when these angles, or one of these angles, is an obtuse angle. So to do that, I'm going to go on to another slide. So what I've drawn here now is a triangle where the angle A is obtuse. That means that it is between pi and pi over 2. It is between 90 degrees and 180 degrees. And it's immediately apparent that if we now drop a perpendicular, as in here, then it is not going to hit the bottom line of the triangle. So instead what we're going to do is we take this line here and we continue it out this way, and then we drop this line here such that we form a right angle at the bottom. And I'm then going to call this height here little h. This side of the triangle here is little a because it faces capital A, and this side here faces the angle capital B, so this side is lowercase b. So now at this stage we can repeat our above argument to derive the sine rule, and what we do is we look at this triangle, this right angle triangle, and also this right angle triangle. So for the first one, this angle here, the angle of this triangle here rather, the angle here is the angle of pi minus a. So again, I'm going to draw it in red, and the angle is pi minus a. So for this triangle, we have that h divided by b is the sine of pi minus a. So h over b is the sine of pi minus a. And at this stage we realize why we earlier looked at the sine of pi minus a, and we showed that this was equal to the sine of a. Similarly, we can look at this triangle here, and we have that h divided by little a is the sine of capital B. So h over little a is the sine of capital B. So this means that h is b times the sine of a, and here h is a times the sine of b. Both of these things would be equal to h, so therefore they're equal to each other. So I'll just pause, make a little bit more room. So therefore, b times the sine of a is a times the sine of b. Is a times the sine of capital B. So therefore, rearranging that, we have that the sine of capital A divided by little a is equal to the sine of the angle capital B divided by lowercase b. And that's exactly the same as the result we had a moment ago, so this completes our proof of the sine rule. You can easily look at this triangle here and extend it to the other angle and the other length. So we've seen that the sine rule holds where angles are acute, and we've also seen it holds where an angle in the triangle is obtuse. And what we now want to do is to move on to look at the cosine rule. We'll go on to another slide. So what we now want to do is to derive the cosine rule. I've drawn again the triangle using the same notation as before, except that at the bottom here, this side of length lowercase c, I've broken it into two parts through dropping a perpendicular here. And I'm calling this length delta and this length c minus delta, so that if I add the two of them together, the deltas will cancel, and I will see that the entire length of this side is lowercase c, which is what we want. The height of this perpendicular here, I'm going to call lowercase h. And now what I'm going to do is I'm going to look at Pythagoras' theorem for this right angle triangle and also for this right angle triangle here. So both of Pythagoras' theorems for these two triangles are going to involve this side, because it's a common side in the triangle, squared. So we're going to be able to get h squared in here, and then we're going to rearrange and get an equality linking the sides of this triangle to the sides of this triangle. So let's first of all write Pythagoras' theorem down for this triangle here. And what we have is that the hypotenuse squared, a squared, is equal to the other two sides squared, so that's h squared plus c minus delta all squared. And for the other triangle, Pythagoras' theorem tells us that b squared is equal to h squared plus delta squared. So what I'm now going to do is I'm going to take this over to this side, I'm going to take this over to this side, and then both of them are going to be equal to h squared, and will therefore be equal to each other. So what we get is that h squared from this equation here is equal to a squared minus c minus delta all squared, and from this equation here, h squared is b squared minus delta squared, so I can just say immediately that h squared, which is equal to this, is also equal to b squared minus delta squared. So now I have an equality here which does not involve h, that this is equal to this, and I will take this term over to this side so it will become positive. So therefore what we have is that a squared is equal to b squared, and I'll now write down this term that I've taken over here, so that's now going to be plus c minus delta all squared, and then minus the delta squared term that we have here. So now I can expand these brackets when I square it, and I'm going to get that a squared is equal to b squared plus c squared minus 2 delta c, that's the cross terms, and then there will be a plus delta squared term when I expand that, but that will cancel with the minus delta squared term here, so I'm not going to write that down. And at this stage, we have almost the cosine rule, but this involves delta as written here. But if we look at our triangle here, we see that the cosine of A is delta over B. So that means that delta is B times the cosine of A. So delta is B times the cosine of the angle capital A. So therefore, what we have is that A squared is B squared plus C squared minus 2, and then delta is B times the cosine of A times the C, so let's put the C first, times the cosine of capital A. And that we recognise as being the cosine rule. So what I now want to do is I want to consider the case where the angle is an obtuse angle and show that again we can still derive the same formula. And I'm going to do that on another slide. So to finish this video, what I want to do is to consider the case where the angle A is obtuse and show that the same formula for the cosine rule still follows. So what I've done is I've drawn out our triangle. I've chosen A to be the obtuse angle, so it's between pi over 2 and pi, and I have continued this line on until if I drop a line here to perform perpendicular with it, we get this line here, and I'm calling this H. So again, this has been continued straight on until it is underneath this vertex point here, and I've dropped a perpendicular. So now we have two right angle triangles in this drawing. We have this one here, and we have this one here. And again, just as before, we can use Pythagoras' theorem. So Pythagoras' theorem for the larger triangle tells us that h squared is equal to the hypotenuse squared minus the lower side of the triangle, all squared, and this lower side is c plus delta. So I take c plus delta and I square that. Similarly, looking at the smaller triangle, I have that h squared is equal to the hypotenuse here, b squared minus this side squared. So we also have that h squared is equal to b squared minus delta squared. So we can rearrange this now to say that a squared is equal to b squared. We're taking this over to here, so it becomes positive. So it's plus c plus delta all squared, then minus the delta squared. Just as before, we can expand the brackets here. So we have that a squared is b squared plus c squared plus the cross terms, there are two of them, 2 delta c, and the delta squared terms again cancel. We have a plus delta squared from here when we expand it, and a minus delta squared from here. Now, at this stage, we look at the triangle again. So what I want to do is I want to replace delta here in terms of the cosine of A. And if I look at this triangle here, which involves the following angle, it involves the angle pi minus A, what I then have is that B divided by, sorry, I take that back, delta divided by b is the cosine of pi minus a. So therefore I have that delta over b is the cosine of pi minus a, and if you remember earlier on where we showed the formula for the complementary angle here, pi minus a, we showed that the cosine of pi minus a is minus the cosine of a. So this is equal to minus the cosine of a. You may be slightly concerned here about the minus sign, perhaps. Delta over b being, of course, the ratio of two positive lengths. What it is that a is an angle here which is obtuse, and that means that the cosine of such an angle is negative. So minus the cosine is overall, of course, positive. So now we can from this say that delta is minus the cosine of a times little b. So we can substitute this into this equation here, and what we get is that a squared is b squared plus c squared plus 2. Now we replace delta, so there's a b, the c is already there in the equation, and there is a factor of the cosine of a, and I didn't change the minus sign. There's a minus sign here, so this sign should be a minus sign. And that completes our derivation. You can see it's very, very similar to the previous derivation. We just drop a perpendicular and we use Pythagoras' theorem on the two right-angled triangles which we have available to us. And we have used this property of the cosine of the complementary angle being minus the cosine of the other. Okay, so we've shown the sine rule and the cosine rule, and we've looked at the cases where the angles are obtuse as well as the cases where there are only acute angles, and we'll finish this video here.